Hello and welcome. My name is Dr. Ren Capes and I'm here to introduce to you the European Union's new European Ground Motion Service, or EGMS for short. Using a remote sensing technology based on the data collected by radar satellites, EGMS provides millimetre scale measurements of ground movement across most of the European continent. I'm not talking about mapping the big metre scale movements of, say, an earthquake or an active landslide, but the tiny, more insidious ground movements of a few millimetres per year that can be precursors to greater motions and that are in fact the most costly to our economy. This is the first of 5 webinars on EGMS, this one introducing the service. The following 4 are thematically based and will cover natural resources, geological hazards, climate adaptation, and urban areas and infrastructure. This is what we'll cover in today's webinar. Why is there actually any need to map ground movements at all? What is the European Ground Motion Service? Some brief detail as to the underlying technology, and then a description of the 3 main EGMS products. I'll then show some very brief examples of what can be done with EGMS data, bearing in mind that there are 4 upcoming webinars that will focus on particular themes. I'll then describe how to access EGMS products, how to learn more, before we end with a live Q&A session. So, let's get started. Why EGMS? So why do we even want EGMS at all? In our daily lives, we assume the ground to be stable, when in fact much of it is in some form of local motion, that is, separate to some wider scale motions such as tectonic crustal deformation. Although some ground motion is fast and obvious, like an active landslide, in fact a lot of the most costly ground motion is at millimetre scale and difficult, if not impossible, to measure. For example, the wide-scale subsidence caused by the clay shrink-swell cycle, or the uplift caused by the flooding of old mines. Ground motions, or rather geological hazards, are in fact ubiquitous across Europe and affect at least 1/3 the population in some way, shape or form. Conventionally, mapping ground motion requires the installation of in-situ devices, whether a GPS receiver or a total station, and this pragmatically restricts the density and area of deployment to a localized feature. As this is expensive, such deployments tend to only be made reactively for a particular project, for example, monitoring the subsidence caused by tunnelling. However, the big news is that Copernicus Land Monitoring Services can now announce the release of the first ever, entirely free of charge, European scale ground motion mapping service. So, what is EGMS? The European Ground Motion Service is the latest offering from the Copernicus Land Monitoring Service. EGMS products are made from the processing of data acquired by the Sentinel-1 radar satellite mission of Europe's Copernicus program. The service provides continental scale measurements of ground motion, presented as a high-density array of points, colour-coded by their ground velocity in millimetres per year, each point also having an associated time series plot. As with all Copernicus services, EGMS products are openly accessible and free of charge to everyone. So, what does EGMS measure? EGMS products provide measurements over time of the millimetre scale movement of ground-based features that just happen to reliably reflect the radar signal back to the satellite. These ground-based features may be natural, such as bare rock, or anthropogenic, such as buildings and infrastructure, and they can make up high-density arrays of EGMS measurement points, each with an average velocity and associated time series. Such products allow us to measure and map a variety of ground motion phenomena, or rather geological hazards, such as subsidence through, say, mining or clay shrink swell, landslides, uplift from, say, underground gas storage, the stability of larger scale infrastructure, including bridges, dams, roads and rail, power stations, also the surface effects of tunnelling and underground construction. EGMS will help build awareness of geological hazards across Europe and support more sustainable choices in planning and development and in the management of land resources, buildings and infrastructure. Let's take a quick look at the technology behind EGMS. The data for EGMS products is collected by the Sentinel-1 mission, comprising two identical radar satellites in a near-polar orbit 180 degrees apart. They are in this configuration to double the frequency of data collection. Radar satellites are active inasmuch as they emit pulses of electromagnetic radiation and then record the strength of the return, its time delay, and importantly for our purposes, the phase, that is, the angle of the signal's sine wave as it returns to the satellite. The active nature of the instrument and the wavelength of the radar signal means that data can be collected at night and through cloud cover, so acquisitions are 100% reliable. EGMS products are made from hundreds of repeat image acquisitions over the same locations across the whole of Europe. EGMS products are made by processing stacks of Sentinel-1 radar imagery that are taken over the same place over time. The mission acquires data over Europe typically every 6 days, but 12 at worst. I ask you to imagine our satellite orbiting the Earth, collecting dozens of images of the same place over time. During one orbit, it images a building. The next time the satellite comes over, the building has subsided, and this is sensed by the satellite as a difference in the phase of the returning signal. It is this interference in the phase between images that gives us the name interferometry. In EGMS, thousands of images acquired since 2015 all over Europe have been processed. In this special interferometric processing, arrays of points are identified that represent features on the ground against which we can make these precise phase change measurements. Not only do we know the average velocity of each point, but we also have the time series plot for each one, and this reveals motion trends, accelerations, when movement started and stopped. So what do these data look like? Here we see EGMS data points superimposed over an optical background. They're colour-coded by their velocity, green being stable, cold or blue colours moving towards the satellite, and warm colours, red and yellows, moving away from the satellite. Two key points. By definition, these ground features, or EGMS measurement points, must have been spectrally stable throughout the period represented by the dataset, otherwise the algorithm would reject them. Therefore, EGMS data is much denser over built environments and much more sparse over more rural, vegetated areas where the signal decorrelates between satellite images. The other thing is that we have no choice as to what ground features act as reliable reflectors. We can only filter out noisy data. So, in terms of point coverage, EGMS products are made by a rather serendipitous process. The point I want to draw your attention to with this slide is that EGMS data is acquired in what we call the satellite's line of sight. As radar is a ranging technology, the instrument needs to look to one side to build a two-dimensional picture. The significance is that the orientation of any displacement on the ground is projected onto this line of sight, and so the actual direction of movement is ambiguous without some other form of information. However, in EGMS we have a workaround. Our satellites are configured in a near-polar orbit, and although they might take 80 minutes or so to complete an orbit, the Earth is spinning beneath, and so it actually takes a week or so to acquire a repeat image of the same place. As this graphic illustrates, half the time the satellite is travelling from north to south, looking west. The other half, it's travelling from south to north, looking east. Data for EGMS is therefore acquired in two discrete, nearly opposing geometries. In EGMS, these two geometries, called ascending and descending, have been further exploited to produce purely vertical and horizontal ground motion layers. This removes the ambiguity of the direction of displacement that we have with a single line of sight. Now let's take a look at the actual EGMS products. There are three main EGMS products: basic, calibrated and ortho. Basic and calibrated products have two layers each, acquired at different geometries to provide near opposing look angles. The ortho product also has two layers, made from the calibrated product, to provide purely vertical and east-west horizontal motions. In all products, the time series plot revealing ground motion trends is available for every measurement point by point and click. I'll describe each product in more detail. The EGMS Basic product includes all measurements of ground motion in two discrete datasets, ascending and descending. Basic products precisely measure local motions at full resolution, but do not capture larger scale displacements like isostatic rebound from glacial retreat or movement caused by plate tectonics, because these are relative measurements. They are relative to a stable point within the same dataset. Plus, any displacement is projected onto the satellite's line of sight. For these reasons, these data might require more expert interpretation. Production of the EGMS Basic product is a necessary first step to produce the more advanced and useful calibrated and ortho products coming up next. The calibrated product is essentially the same as the basic product, full resolution, except measurements are tied to a GNSS reference frame that has been newly created for the service. The localized basic measurements are superimposed onto the larger scale motions caused by, say, tectonics as measured by the GNSS framework. Thus, velocities and time series in the calibrated products are, in effect, absolute, and so integration with other geospatial datasets is simplified. The calibrated product is considered more user-friendly than the basic product, and we anticipate seeing the widest use. The ortho product is made up of two layers, one showing just vertical motions, the other just east-west horizontal motions. The ortho product is made from the ascending and descending layers of the calibrated product. In the horizontal domain, only east-west motions are provided. This is due to the orientation of the satellite look angle being mainly from the east or west. The ortho product provides an unambiguous direction of movement and so is useful in areas of steeper topography or landslides, or anywhere with ambiguity over the orientation of displacement. Plotted on a 100-metre grid to coincide with other Copernicus datasets, the ortho product may be easier to understand and interpret than the higher resolution calibrated product. Looking at the periods covered by EGMS data, the initial EGMS baseline datasets were released last year and cover a nearly 6-year period from January 2015 to December 2020. So these datasets show the ground motions that have occurred within that time frame and only within that time frame. The plan is to update EGMS data annually in every third quarter covering the preceding year. The first update, taking the service to December 2021, has now been released. Although an incredible groundbreaking service, EGMS products do have some limitations. For example, coverage of measurement points. The INSAR technique relies on ground features being stable over time, and as the ground is covered by all kinds of things, some stable, some moving around or changing, the coverage of EGMS measurements is not continuous in space. As mentioned previously, the coverage is most dense in built environments and most sparse in rural vegetated areas. Next, spatial resolution. EGMS products are made from Sentinel-1 data that are captured from a ground cell measuring approximately 20 meters by 5 meters. Only one measurement can be obtained from each ground cell, and so this rather limits the size of features that can be mapped. On top of this, there is also some ambiguity as to the exact XY location of each measurement point. Although EGMS measurement points have a millimetric precision in terms of measuring displacement, there is paradoxically a meter scale ambiguity over their exact XY location. A measurement might also be the result of multiple bounces before the signal returns to the satellite. It is therefore not safe to say that this measurement point is on the corner of that house. It's far better to trust clusters of measurement points displaying similar behaviour and that might contain the feature of interest. Finally, north-south ground motions are not measured by the EGMS system due to the near east and west look direction of the satellite in its corresponding ascending and descending orbits. Let's now look at some actual real-life applications of EGMS. This is only a very brief look, as we have 4 upcoming webinars that each focus on a different thematic area of application. This first example focuses on the effects of the exploitation of natural resources in the Netherlands. Note, this example is made from the vertical layer from the EGMS ortho product, so is just seeing purely vertical motion. The area marked with an A is within the infamous Groningen gas field, the largest in Europe, where removal of underground gas has not only caused subsidence but even earthquakes. The time series plot in red is compiled from an average of over 1,000 points that are encompassed by the square. The average of all these points reveals subsidence occurring at a rate of around 7 millimeters per year, with a total of around 2 centimeters over 5 years. The area marked with a B relates to the Veendam salt deposits, where solution mining is causing subsidence. This time, the time series plot shown in green is for just a single point that is subsiding at a rate of around 26 millimeters per year, with a total displacement of 8.5 centimeters over 5 years. Next, we're looking at geological hazards. This example is of a landslide in Italy and is made from the EGMS calibrated data. It's useful for two things. First, it shows the utility of EGMS data in mapping landslides, but it also shows the sensitivity of the two opposing satellite look directions of the ascending and descending datasets. In the left-hand image, the satellite is looking east from the west, and so material sliding down this western face is moving towards the satellite, depicted in blue. Meanwhile, in the right-hand image, the satellite is looking east from the west, and so the same material is moving away from the satellite, depicted in warm colours. The datasets, in fact, validate each other. Next, climate adaptation. Here we're looking at the effects of sea level rise where coastal communities affected by subsidence might be prone to increased flood risk. This harbour town in Denmark is among the most vulnerable in the country. Being only 2 metres above sea level anyway, the town can't afford to subside in the face of increased storm surges plus a general rise in sea level. EGMS products provide long-term national coverage and can help to better understand and analyse subsidence processes that might exacerbate the effects of climate change. Here, we're looking at the use of EGMS data in urban scenarios. In this example, we see central London with a portion of the River Thames mid-left. The large ringed area of subsidence is due to tunnelling for a major new sewerage system. We can see the broader effects of this on the surrounding property in the area. We can also see a line of subsidence that accords with tunnelling for the extension to a metro line. Remembering that these data in the main map show averaged velocity, it can be useful to look at the time series plots to gain a better understanding of when any motion might have in fact started or stopped, and this could be useful, for example, for insurance. The time series plot shown is an average of all the points in the polygon. You may notice 2 lines of data in the time series plot. This is because we're seeing the average displacements as measured by both ascending and descending data. This example shows the wide area utility of EGMS data in monitoring large-scale networks, in this case a road, but this could be a railway or the alignment of a gas or water pipeline network. Here we see a portion of Spain's main A7 auto route where it crosses a large area of land subsiding due to groundwater abstraction. Perhaps this 8 centimetres of displacement over 6 years is no issue in the middle of the bowl, but EGMS data can be useful at revealing where motion might be more differential and perhaps damaging. This area is in fact well known for its subsidence due to water abstraction, with the main city Murcia severely damaged during the 1990s when over €50 million was spent on remediation. Radar interferometry has in fact been used over the area to map the extent and magnitude of deformation for more than 2 decades. This final example shows EGMS calibrated data over a reservoir and dam in eastern Spain. There is deformation visible across the width of the southern shoreline, with a clear localised focus beneath the dam itself, moving in the range of around 10 millimetres per year. Many reservoirs and dams can be seen at once in EGMS data, perhaps offering support to a more systematic approach to the monitoring of such large-scale and widely spread infrastructure. You may notice 2 lines of data in the time series plot. This is because at this zoom level, the point and click to bring up the time series covers more than 1 point. If you zoom right in, you can of course select individual points. How to access EGMS data. The EGMS Explorer viewing tool, available within a browser at the address shown, allows you to view, analyse and download the EGMS data. In the top right corner of the Explorer is a toolbar that provides a number of functions, including point-and-click time series analysis for every point, averaging of point clusters, the plotting of cross-sections and full export control. No registration is required to use the Explorer. Download of data from the archive does require registration using the EU login system as shown in the next slide. Here you can either create a new account or log in with an existing EU login account. How to learn more. For those who'd like to know more, there is stacks of documentation available from the EGMS site. This slide shows a selection of perhaps the most useful to users. I'd also like to emphasise the existence of a dedicated EGMS help desk to provide support and answer any questions. It's also there to record feedback about the service so that improvements can be made down the line. Upcoming webinars. Finally, just remember about the 4 thematically based webinars coming up. Registration will be open a month before each one, so please be sure to keep an eye on the EGMS webpage. And that concludes my presentation. I hope it was useful, and I remind you that this presentation is available from the EGMS site. I thank you for your attention.